Okay, last time we did section 4.4, which was the last section of the design of experiments, design of studies chapter. Any remaining questions over any of that material before we go on? Everybody knows how to tell an observational study from an experiment?
Could you give us a few examples, like just to refresh your memory?
Okay. Remember when I talked about doing an experiment where I recruited people who were down in the gym working out, and I recruited people who were at McDonald's eating, right? And I then compare their cholesterol levels. Is that observational or experimental? You're saying it like a question.
Observational?
Good. Observational. And why is it not experimental?
Because you are giving them
Because I'm not imposing any kind of a change, right? I'm not imposing a treatment on the subject or anything like that. So that's the hallmark of an experiment. So make sure that you're able to do just that. You're able to take a scenario and read the paragraph and figure out the basics of the design of the study. Is it experimental or observational? If it's observational, is it case control or cohort study, those kind of things? Do they use blocking? Do they use blinding? All those terms. Those are things that you'll have to pick out of a scenario and answer questions about. Okay? Anything else? All right, then we will go on to the most fun chapter of probably the whole book, and that is probability. Now, what it says is going to happen in the syllabus, what it says is today is 5.1 and 5.2. And I was able to do that this morning in my first class, but I flew. So it's going to go fast. But then you'll have problems to work on to practice it, and it'll make sense. Wednesday will allow you to ask questions and that kind of thing. So most days when I ask for questions, I don't get any, but Wednesday I fully expect we're going to get some. So we're going to start with the basics, a lot of terminology. Once we get that, we're going to do some simple probabilities today, and it'll get more complicated on Wednesday. But probability, as a definition, probability quantifies uncertainty. Let's spell that out. Okay? So when you have the book calls it a random phenomena, and that's too hard for me to spell, so I call it random procedure, or a random event of some kind. Like if I flip a coin, that's a random procedure. Okay? Probability quantifies the uncertainty in the outcome that you'll get. Okay? So, first thing we need to define is a sample space. The sample space is the set of all possible outcomes. Okay? So let's define, boy, my markers are really having some trouble today. Let's define a random procedure of flipping a fair coin. And I just happen to have a fair coin with me. It's a nickel. If I flip this coin, what's the probability it comes up heads? I heard 3 different answers that all meant the same thing. And you can say it a lot of ways. I heard somebody say 50-50. I heard somebody say 50%. I heard 1/2. I didn't hear 1 out of 2, but that means the same thing, right? What's the sample space if I flip a fair coin? The way we denote sample space is with a capital S, and then it's set notation. Now everybody in here probably at some point in your mathematical lives has had a little bit of set theory. You might not have had very much, but you learned what a set was, and intersection of sets, union of sets. Have you heard of these terms before? Okay. What are my possible outcomes if I flip a fair coin? Heads or tails. So I'm going to denote that with an H and a T. And that's typical. We'll typically use like capital letters, single letters to denote a particular outcome or a particular event. I could say, let's let H equal the event that it lands heads. Okay. Now, intuitively, everybody was able to figure out that the probability of H, which we write like this, probability of H, so capital P, parentheses, and then something in the parentheses, means the probability of that thing. Excuse me. Everybody's able to figure out that's 1/2. We will always use probabilities like proportions, not percents. Okay. I will say them as percents, but when I write it or do math with it, I always will write it as proportions. Numbers between 0 and 1. Okay? So the probability of any event, call it X, must be between 0 and 1. What does the probability of 0 mean? Not going to happen. So this little arrow means implies. So probability of something equals 0 implies it cannot happen. Okay? Or will not happen. Probability of 1, it's certain to happen. Okay? Most probabilities that are interesting are in between those two extremes. Okay? Like, for instance, the probability that you go down to the local convenience store, buy a Powerball ticket, and win the Powerball lottery. What's that probability?
1.5 million people in the United States that bought a Powerball.
No. But that's what a lot of people think. What she said is it's 1 out of however many win. That's like if they did a drawing. Like if you buy a raffle ticket, right? However many raffle tickets are sold, your probability is 1 out of however many were sold. But Powerball doesn't depend on that. It depends on you matching the numbers that are randomly drawn from a bin. And there could be 50 people that match. There could be nobody that matches, right? So the probability doesn't depend on how many bought a ticket. Even if you're the only one that buys a ticket, you may not win.
Your probability in the Powerball depends on how many combinations there are of all the different numbers.
Exactly.
In the millions.
The probability of winning the Powerball lottery depends on how many possible combinations there are of numbers. And I can just tell you this, it's a lot. There's a lot of combinations. The Powerball probability of win in the Powerball is 1 in 146 million approximately. There's some other numbers here, right? But it's about 1 in 146 million. That doesn't sound that bad, does it? Right? Well, one of the things that you have to understand, if you put this in decimal form, what's the decimal equivalent of that? So let me do it on your calculator. Take 1 divided by 146,000,000.
6.849 to the negative 9.
6.849
Times 10 to the negative 9.
and it says E -9 like that. And so this is something that you need to start getting used to on your calculator. It goes into what's called exponential notation, sometimes called scientific notation. So what this means is 6.849 times 10 to the -9th power, which means move the decimal 9 places back to the left. So you take this number, move it 9 places. Let's see, that would be 1, 2, 3, 4, 5, 6, 7, 8, 9. There's your chance of winning the Powerball lottery. Is it 0? No. Is it pert near 0? Yeah. You ain't winning the Powerball lottery. Right? I ain't spend too much time on this, but this is, I always think it's a good thing. Numbers like this, huge numbers like this, or really tiny numbers, are hard for us to get our brains around. So I always need some kind of concrete example. So think of it this way. Suppose the jackpot happened to be $146 million, and it gets above that sometimes. But just suppose that. Suppose they paid you in $1 bills, right? If you took those 146 million $1 bills and you laid them end to end, how far do you think they'd reach? Well, it goes like this. I'll give you the abbreviated version. Let's say we started here in Topeka and we went west on I-70. Do you think you could get to LA? Yeah, you can get to LA. And you can go from there up to Seattle, from there to Maine, from there to Miami, Florida, from there to Phoenix, Arizona, to San Diego, back to Chicago, back to Topeka. It's about 14,000 miles that those dollar bills, end to end, touching each other, would reach. Now here's your chance of winning the Powerball lottery. Start walking. Follow that trail, and at that point in time when you're feeling especially lucky, bend over and pick up a dollar bill. If it has a red dot on the back of it, you just won.
How many of those dollars have red dots on them?
One. There's only one of them. For every dollar, let's say, oh, well, I spent $5. I bought 5 tickets. Okay, now 5 of them have dots. You still ain't winning, right? You multiply your probability by 5 and not much changes, right? So that's the probability of winning the Powerball lottery. Really, really small number. So probabilities near 0 means it's very, very unlikely to occur. We will use that concept as we go into hypothesis testing and doing statistical inference. We will compute probabilities of certain sample values and then say, well, the chance of that is really, really small, therefore I don't believe that to be true. Yeah?
And how do you guys explain people winning it twice?
How do you explain winning twice?
You're statisticians. You're saying it's like hardly ever that you
Right.
do it.
It's almost impossible that a person could win. But yet there have been a few examples where somebody has won twice.
Right.
And it's just astronomical probability, but you know, things happen. People say, well, if nobody's going to win, how come somebody always does win? Well, because 300 million people buy a ticket, right? Or whatever. And you do it enough times, then somebody's going to win. But the probability that you pick a person and then say, follow that person, see if they win, it isn't going to be that person. Eventually somebody will, but and winning twice is astronomical. It's a very, very small chance. But okay, so back to the basics. That's enough of that for a little bit. Back to the basics. Let's roll a 6-sided die. A fair 6-sided die. First thing I want you to define for me is the sample space. Write down on your piece of paper what you think the sample space is for that random procedure. Rolling a 6-sided die one time. Caitlin, you looked up first. What did you put?
1, 2, 3, 4, 5, 6.
1, 2, 3, 4, 5, 6. Very good. There's the sample space. The set of all possible outcomes. Now, let's define the event 1 as rolling a 1. What's the probability of a 1? 1 out of 6. Hey, you guys are good at this. I think we don't even need to do this yet. Well, how did you get 1? How did you get 6?
There's 6 sides.
Okay, there's 6 sides to the die, meaning 6 things in the sample space, right? So what this is the number of ways the event can happen. The event is rolling a 1 divided by number in the sample space. Or another way to think of that, a little less stat speak, is the number of possible outcomes. Okay? Let's define an event E. That you roll an even number. What's the probability of E? 3 out of 6. Everybody see that? Because there's 3 things in the sample space that make this event come true. So the number of ways the event can happen is 3, divided by the total number of possible outcomes, which is 6, which you can then reduce to 1/2 or 0.5. Okay? So far, so good. What's the probability of, well, wait a minute. Let me define another event. I'll call it L. The event L is you roll a little number. L for little. A 1 or a 2. Okay? That's an L. What's the probability of L? Well, there's 2 ways that can happen out of the 6. So 2 out of 6. Right? Which does reduce to 1 out of 3. Now, what's the probability of not L? Which we write as L, a little superscript of a C. That stands for complement. So A superscript C means a complement. And you read it as not that event, right? So what's the probability that you did not get a little number? 4 out of 6. What do you notice about the probability of L and the probability of L complement? They add to 1. And they will always add to 1. So that's one of our rules of probability. The probability of A plus the probability of A complement must equal 1. If A doesn't happen, it has to be the leftover probability from when A does happen. Which you can manipulate this algebraically to say that the probability of A is equal to 1 minus the probability of A complement. We'll use that little equation sometimes because sometimes it's really difficult to compute the probability of something, but it's really easy to compute the probability that it doesn't happen. For instance, suppose I flip my fair coin 10 times. What's the probability that I get at least 1 head out of those 10 flips? Oh, I don't know. But what's the complement of at least 1 head?
9 tails.
What's that?
9 tails.
No? Almost. She said 9 tails. But what's the complement of at least 1 head? If you didn't get at least 1 head,
9
9
out of
heads.
10.
10.
10 tails. Not 9 tails, but 10. All 10 had to be tails. That's the only way to flip a coin 10 times, and you don't get at least one head among those 10 flips, right? The probability of getting 10 tails in a row, that's fairly easy to compute. I'll come back to that. I'm not going to compute it right yet, but I'll come back to that. So sometimes it's much easier to compute the complement of an event than the event itself. And you can just use the complement rule to figure that probability. Okay? So let me do this. What's the probability of L or E? And what does the word "or" mean?
Either one or the other.
Means that L could happen and make that true, or E could happen and make that true. Or they both could happen, right?
4 and 6.
How many numbers are there that are either even or little? Well, I'm going to underline. These are my little ones. These are my even ones that aren't already underlined. So I got 4. The answer to this is 4 out of 6. Right? What's the probability of L and E?
1, 6.
What does the word "and" mean? It has to meet both of them at the same time. So it has to be a little number and it has to be even. So there's only one number that does that, and that's the 2. So that one is 1 out of 6. Okay? Or is synonymous with union in set theory. And the word "and" is synonymous with intersection. Have you heard of those terms before? I'm erasing my sample space here, and it's too late, I already did it, but I want it back. But just look at it in your notes. I'm going to draw something called a Venn diagram. Remember these? Now some people, when they think Venn diagrams, they think, oh, I hated these. Other people, ooh, yeah, these are cool. And it's just a matter of organizing information. If you like Venn diagrams, then great. If not, there are other ways to do the same thing. We'll do tree diagrams, we'll do contingency tables, and Venn diagrams. Those 3 things give you different tools to do the same thing. Pick the one you like. So the way we do a Venn diagram, you draw a box that represents the universe, or the sample space. Okay? And then in that box, you draw circles to represent your events. So if my 2 events are L and E, let's call this E and this one L. Okay? Now somewhere in this box, I have to put the sample space, the numbers 1 through 6. So now I just got to figure out where do they fall. So E contains, inside the E circle, I need all the even numbers. So I need 2, 4, and 6 inside this E, right? So 2, 4, and 6. But wait a minute, one of those numbers satisfies L, so it needs to go inside the L circle. Which one is that?
2.
2. So the 2 goes where?
In the center.
In that middle part that's in both circles. And what is that part called?
Over.
Okay, the overlap, but another word,
Intersection.
the intersection of the 2. Where the 2 circles overlap, they are intersecting. So this is called the intersection, which is the word "and." Okay. Now, what numbers are in L but not in E? The number 1. So it goes out there. Anything else is not in either of those, goes outside the 2 circles but inside the box. And that's the numbers 3 and 5. So I'll put a 3 and a 5 somewhere outside the circles. Okay? So the set L and E is L intersect E, which we write with an upside down U, right? So this is intersect or and. L union E, and that's the right side up U, that's union, which is the word or in probabilities. Okay? If two sets do not have any overlap, their intersection is empty, then we say they're disjoint sets, right? Or disjoint events. So, disjoint if the probability of A and B is equal to what? 0. Okay? What's the probability of E? Let me see how I'm going to say this. The probability of E or E complement. Emily did this. E or E complement? 1. That's got to happen, right? You're either going to get an even number or you're not. Duh. Right? You roll it, you're going to get one of those two things. So that's a 1. A Venn diagram helps you compute fairly complicated probabilities, like what's the probability of not being either in L or E?
2.
There's two numbers like that, right? The way you would write that is difficult. Probability of L or E complement. And that looks horrible, and people would panic on a test and go, oh, I don't know how to do that one. If you do a Venn diagram, it becomes fairly obvious. The union of two sets is the OR, so that's all of the region that's inside of either of the circles. Anything that's outside that shaded region satisfies L or E complement. Okay?
So the little box thing is basically telling you everything that's not included in.
Right, it's just, I put that there so that the E, so that the complement applied to the whole thing, not just to the E.
So you can't put parentheses instead of parentheses.
Right. Well, you can, but
It looks weird.
on your calculator, that's the only thing, you only have the one parenthesis symbol, but yeah, it looks weird, so.
Well, would it,
There's brackets and
if you have the probability of L or E complement, what about the L? Is it 2 L and E complement?
So you've had some logic set theory before? You're saying, isn't this the same? This is beyond the scope of this course, but it's fun. L complement and E complement. Is that what you're asking?
No, I was saying that 2 is L and E. L and E, not L or E, right?
Right. 2 is L and E.
So what would be the complement of L or E? It would be, L or E would be 4, 6.
Yeah, the complement of L or E. Okay, forget the complement. L or E is anything in this shaded region.
Okay.
4 numbers.
Okay, I'm
Right.
sorry, I just thought you said just 2 was, and I was confused because I thought you said 2 was just L and E.
No. I might have said that, but I didn't mean it.
Okay.
Now, is this a true statement?
Yeah.
I know what you're thinking. Oh, God. Is it true? The complement of L intersect, so and, the complement of E. So it has to be both outside of L and outside of E. Does that give me the same thing? Yeah, both of them are 3 and 5. So this is, you get this in higher level math classes and set theory and all that stuff, but that is one way of computing probabilities. But Don't get hung up on that. Okay? Well, seems to me like you guys are awful good at this stuff. So when that happens, it's my job to try to make it more complicated. So, here we go. We said that if I flip this coin, I have a 50-50 shot of getting heads, right? Okay? So if I flipped it, say, 10 times, how many heads would I get? Come on! 5, right? Yeah, it's a trick question. Why do you say it's a trick question? You might not get 5. You expect to get 5, but you might not exactly get 5. Would it surprise you if I only got 4? Would it surprise you if I only got 3? Would it surprise you if I only got 2? And now all of a sudden, yeah, that would surprise me. Or 1 or none. If I flip it 10 times, I don't get any heads. That would be surprising. Is it impossible? No. It is possible, but the probability goes down, right? Now, if I flipped it 100 times, would it surprise you to get 40 out of 50? Would it surprise you to get 30 out of 50? Okay. Well, I forget now. What was the cutoff when I was flipping it 10 times? You got surprised at 2, right? But at 3 you weren't surprised, right? Would you be surprised at 30 out of 100 heads? You said a little? Okay, let's flip it 1,000 times. We got nothing else to do. Let's flip it 1,000 times. Would it surprise you to only get 300 heads? So the same proportion, 3 out of 10, 3/10, 0.3, that didn't surprise you when I flipped it 10 times, now you say it would definitely surprise me if I did it 1,000 times. What are you intuitively picking up on? The more times you do it, the closer it should get to the true probability. That's known as the law of large numbers. Okay. The law of large numbers, if you repeat a random procedure a large number of times, the proportion of, I'm going to just use a generic word, proportion of successes. So if you're talking about flipping a coin, you might say, well, let's count the number of heads. So getting it to land heads is a success. If I'm rolling a die, I may say, well, let's call a 1 a success, or whatever. But just, if you repeat a random procedure a large number of times, the proportion of successes will approach the probability, the true probability of success. Okay? Earlier today I used the example of batting average. Right? Everybody know what batting average is? Some of you are shaking your head no, but just number of times that you come up to bat and then how many hits you get. Right? So if you come up to bat 4 times and you get 2 hits, you're batting 50%. We say you're batting 500, right? And that they just take, they lose the decimal, so it's .500, so they call that batting 500. So when you hear he batted 390 for the season, for the season, like George Brett did, then he got .39 was his batting average, right? Now, if you've only come up to bat twice, what are the only possible values for your batting average? 100.
50.
Well, actually 1,000. Batting 1,000, or batting 500, or 0, right? So 0, 0.5, or 1. Right? But as the season goes along, you get more at bats. That batting average stops fluctuating so much and settles down to the true probability. So you'll see graphs in the book that fluctuate wildly for a while, and then they start to settle down, and they'll settle down to the true proportion. I'll call it P, right? The true probability. That's the law of large numbers. Okay. Okay. Now, something else to think about. I don't have a, I usually do this with a thumbtack, but I don't have a thumbtack in there today, so I'm going to improvise. See this clip? If I throw this clip up in the air and let it land on the floor, it can land like that, which I'll say is on its side, or it can land like that, which is on the end of it, or I count that, which almost never happens, but I count that as also on the end, right? So, on its side or on the end. What is the probability of S for side, that it lands on its side? Well, what's the sample space?
2.
Okay, that's, most people will answer that way. I said, what's the sample space? And about 5 people said 2. Now, the sample space is a set. So the sample space is the set of, it has 2 outcomes in it, lands on its side or lands on its end. I'll call those S and E. So there's the sample space, right? It has 2 things in it. So what's the probability that it lands on its side?
You have to take into account the surface area of the 2 sides. It's more likely to land on its side because.
Just answer the question.
One aspect.
What's the probability?
1 and 2.
1 and 2? Okay. So if I flip my thing 10 times, would it surprise you if I only got 4 on the end? Or 3 on the end? Or 2 on the end? Or 1 on the end? Where would you start to get surprised?
1.
1. You were surprised at 3 a minute ago with the coin. Okay, here we go. Ready? On the end. Okay, keep track. We're going to do this 10 times. Landed on the end. Ready? Side. 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 How many flips is it?
6 out of 7.
Side. Some of you may not be able to see it, but he'll tell you if I lie. Side. How many was that? One more? In.
I only got 9.
Okay, one more. Side. So we got
8 sides, 2 ends.
probability of side as estimated using what we call the relative frequency approach. Means just do it a bunch of times and count how many successes you get. We got 2 out of 10, which is 0.2. We estimated that it should be 0.5.
That's the wrong one.
I'm sorry, yes, side is 8 out of 10. I did E. Thank you. 0.8. We estimated that it should be 0.5. We got 0.8. Does that surprise you? That's not convincing enough? That it isn't really 0.5? Okay, how about if I combine my data with the 10 flips I did in my earlier class? They were convinced because I got 10 out of 10 sides there. So for combining data, we now have 18 out of 20,
9. 9.
right? Which is 0.9. Does that make you think, well, maybe it's really not 1/2? He says, closer, I'm getting convinced. Side. Side. Tell me when you're convinced. I'm getting tired. Oh, and end. The point here is the true probability can't be done like this. It isn't 0.5. Why not? Because the two elements in the sample space are not equally likely outcomes. In a coin flipping, they are equally likely, right? You flip a coin, it's equally likely to land heads or tails, right?
Isn't there always a chance it's going to land on the end?
I was wondering if there'd be somebody that would bring that up. I should have known it'd be you. Is there a probability it would land on the edge?
Very, very small one.
I guess theoretically, if I throw it up and let it bounce and settle, right? But if I throw it up and catch it, then I'm forcing it to be either heads or tails. So that's the scenario I'm picking, right? So it is balanced, as long as it's balanced coin, 50-50. But if it's not equally likely outcomes, the only way to estimate the probability is the law of large numbers. Start flipping that thing, right? Start flipping that thing and see, I don't know how many I added to the 20, but I got one more in and what, 3 more of the others. Anyway, keep doing it till you get a large number, and then whatever it settles down to, that's your probability. Now I'm not going to stand and flip this thing 1,000 times, but that's what you would have to do to estimate that probability. Okay? That's called the relative frequency approach to probability. If you know they're not equally likely, then don't use that formula I put up here a minute ago. Number of ways over total number of outcomes. That won't work. If you don't know whether they're equally likely or not, then don't trust it and go to the relative frequency approach. There's one more way of doing probabilities, and that's called the subjective probability, which some people call a WAG. Stands for wild blank guess. What's the probability that driving home today I get in an automobile accident? There's no way to compute that, right? Being a statistician, I'm always getting, not always, but a lot of times I get people who walk up to me, hey, what's the chance of that? You're a statistician. What's the chance of that? You can't compute a probability like that. They ask the bizarre things. So you do subjective probability. What's the weatherman do? 20% chance of rain today. Can you set up the sample space? It either rains or it doesn't. There's 2 things in it, so there's a 50% chance of rain.
Well, that takes they have a little chart. I took meteorology.
Okay, so what do? They do charts and models and that kind of thing, and they come up with a way of assessing that probability. Can they use the relative frequency approach?
No.
No, you can't say, well, let's repeat this day a whole bunch of times and see how many times it rains.
Sometimes they do that. They repeat the day the year before.
But they do it with computer simulation, right? Say, if the conditions were exactly like they are at this moment, I can tell a computer to repeat that and see how many times the computer model, and then they do probabilities, but it's subjective, right? So 3 different ways to do probabilities, which can lead to wildly different results. Okay, now let's talk about another concept of independent trials. Flipping a coin one time, we call that a trial. So repeating a random procedure, each repeat is called a trial. So for trials to be independent, what do you think that means?
They don't affect each other.
They don't affect each other. So if I flip my coin, does the outcome of the flip on the first time affect the outcome on the second flip?
No.
No. But what if I flip it 9 times, it comes up heads every time? Then the probability of tails on the next flip would be higher, wouldn't it? Because tails is due, right? Nope, it's still independent. The probability is still 50-50. Right? So that's a common misconception that, you know, if it's come up a certain way a bunch of times in a row, then the other one is due, so I'm going to put more money on it happening, or, you know, whatever. Don't do that. Right? Probability doesn't change. They're independent events. Okay? So, can you give me an example of events that are not independent?
Pulling a colored marble out of a bag and not putting it back in when you're done.
Okay. I'll simulate something kind of similar to that. Here's a deck of cards. I know it's in here somewhere. Here it is. See my deck of cards? I'm going to shuffle it. And I'm going to have Logan here draw a card. Draw a card. Well, don't let me see it. Okay. Did you look at it?
Yeah.
Okay. Now, what's the probability that he just drew an ace?
4 of
4 and
52.
52.
4 out of 52. Okay? Now, take my deck. Amy, you're playing. Draw a card. Okay? Did you look at it? She's looking at an imaginary card. What's the probability she just drew an ace?
If
3
his
of
was an
52.
ace, it's 3 of
What'd you say? 3 out of
50. Oh, 51.
3 out of 51. What'd you say? 4 out of 51? Which is it?
Because you don't know if his was an ace or not.
Oh, true.
So what you're saying is that her probability, what's the word? Depends on what he got. So are they independent trials?
No.
No. If the outcome of one event depends on what happened on another event, then they're not dependent trials. And the key there was sampling with replacement versus without replacement. Right? I didn't let him put his card back, and I had her draw. Had I put his card back, reshuffled the deck, then her probability is still 4 out of 52. So the probability didn't change. So they would be independent events. So with replacement gives you independent trials. Without replacement gives you dependent trials. Okay? All right. Suppose I flip a coin 3 times. We're going to learn something called a tree diagram. Okay? What's the sample space of possible outcomes if I flip a coin 3 times? And I'm not interested yet in number of heads, number of tails. What I'm interested in is just the outcomes. Like if I get 3 heads in a row, there's my outcome, HHH. Right? How many total outcomes are there?
It's the amount of times you do it times the amount of.
Well, I got 3 flips, right? I got to fill in each of those blanks with either an H or a T. So there's 2 ways to fill this one in. Since this one's independent, I got two left and 2 left. So I multiply those together and I get 2 to the 3rd power, which is 8. So there's 8 possible outcomes in my sample space. I'm not going to list them all because I'm running out of time, but there's another outcome, right? Well, a tree diagram is a way to summarize this. If you got heads on the first flip, then you can still get heads or tails on the second flip. And so on. So you can represent every element in the sample space as a branch on this tree. The top branch is HHH. Next one down is HHT, and so on. So what's the probability of getting HHT? Well, how many branches have HHT? No, that specific order. Order matters. HHT.
1 and 8.
There's only one of them, and that's this one right here. It's 1 out of 8. Now that only works number of outcomes that make the event happen over total number of outcomes. It only works if they're equally likely. Are these going to be equally likely?
Yes.
They are here because they are independent trials and they're equally likely, heads and tails are equally likely. If I had a biased coin and it was 40% heads, 60% tails, then this wouldn't be 1 out of 8 because you'd be more likely to end up in the bottom half of the tree. Right? So that's a tree diagram. I did not have time to get to the addition rule or the multiplication rule, but read them yourself. The homework problem does involve 1 or 2 of those, but in the next section he redoes them anyway for dependent events. So I don't really like to do it in this section anyway because I don't want you having 2 formulas. So 5-1 and 5-2 together as one homework set will be due Wednesday night. All right? We'll see you then.